All right. Did somebody ask me to be absent today? Hold on a second. Let's check that real quick. Tuesday the 9th. That's Chase. Okay, so that's not today. Very good. So we're expecting a full house today. Are we? Questions here. Okay. It was Sam who was missing. Very good. Let me see. Let me quickly show what the latest course documents, syllabus look like, to get a bearing about where we are and the homework assignments and so on and so forth. So today is February the 4th. This is the 8th class time for us. Last lecture, I had a tutorial 4 put in there, but I removed tutorial 4 in favor of actually doing a little bit more on that and leave it to next Tuesday. So I shifted the tutorial 4 assignments, meaning that whenever there's an assignment as tutorial, you're supposed to actually at least review it by the assignment due date. So I made that to be next Tuesday to 9, and you'll get that before then. And that's when the next homework problem actually is due, which is homework 3, which is due also on next Tuesday. What we're going to be doing today is we're going to do the failure criteria lecture, and I put tutorial 4 again here and tutorial 5. I'm going to jump into tutorial 5 today, and then doing the tutorial 4 for you guys will be easier. I may not be able to do it in class, in which case, if anybody joins me, I will do tutorial 4 during the office hour on, I believe, Monday. So we do have a Monday 8 office hour. So this is where we are right now. So we're going to look at the failure criteria so that we will complete the stresses and stress design. And then we're going to go to stiffness design, and we're going to look at elastic properties, material property design for stiffness. All right, with that, this latest version of the syllabus is actually on Blackboard. So you can look at this yourself, and that puts us, I guess, present day, last day to drop is the 15th of February, and we'll have 2 more lectures before then, which is the 9th and 11th. All right, so that's the syllabus situation. So let's go to the lectures and talk about what I'm going to be talking about today. And that is, for the stiffness properties, failure, lecture 6, which is also on Blackboard. So this is what you're going to be talking about today. And under this, we're going to very quickly look about failure of isotropic layers, orthotropic layers, and then very quickly laminates. So this is content. This is incidentally the topic, the least favorite topic of mine. I literally hate the topic of strength. And to explain the reason, I will put my first chart. Bullet number 1 says no sound analytical foundation for strength determination exists, or something along those lines. There are empirical relations based on stresses or strain analysis and experimentation. And it's typically developed by either limiting the strength of individual plies with different levels of stress, and typically avoids or ignores the interaction of stresses between different layers and potentially things that's happening internally that so complicated that we really have no practical analysis to perform. And then on top of it, it is not quite clear what damage does with strength. And failure is typically not sudden or specified at one load level. We just have to make a bunch of assumptions about it. So it's a really messy topic. But we are engineers, so we'll have to do something about it. And the assumption that we make is stresses induced in a layer can be decomposed along the fiber direction and perpendicular to the fiber direction. And then we look at what fiber does, whether it breaks or what matrix does. And then based on that, we also make an assumption if the matrix breaks, this may not be the failure, that we wait for fiber failure. And then on top of that, if fiber failure occurs in one ply, we may say, oh, this is just the first ply failure. Unless other plies fail, nothing happens. Or we say, as long as the first ply fails, we stop. So there are a lot of assumptions that goes into this. That is the reason why this is one of my least favorite topics, because it's just one assumption another, and then invoking one engineering approximation after another. This is on top of all the analytical work that we do. And we make assumptions, but they at least are based on some sound engineering knowledge. These failure assumptions sometimes we really don't have an idea. Everything might be, in fact, everything is at the lowest scale is micromechanically governed. A material fails because typically there's some structure in the material fiber, some crystal structure in the matrix, some voids, defects at the micro level that initiate something. And those cracks grow and then cause either the fiber or the matrix to fail. In fact, the reason why we like composites is this fuzziness, that the fiber is so small that there is not enough room for sometimes micro-level cracks happening within the fibers. And when they happen, it happens in such a small scale that stresses recover right away around the fiber break. And you don't lose strength by failing one single fiber out of millions and millions of fibers. Okay, so meaning that those failures are happening all the time, anyways. They're there. It's just there are so many of them that you have to wait for critical level for some of those things to cause failure. So that's my complaints about this failure analysis. But we'll have to do it. So what do? We get inspired by the failure of isotropic materials. We do the same thing. It's not much different in isotropic materials. That the failure is also not a well-established science, but mostly empirical and based on the observations and assumptions. And we look at a single layer. Again, the keyword is plane stress. We are looking at a single layer with a ply thickness T. This is, of course, if it's isotropic, there is no orientation dependence. Some stress state is given with these sigma x, sigma y, and tau xy. So this is the stress state. It's basically and tau xy. Now, in this case, the failure is typically categorized based on the material type into one of two forms. It's either by yielding, excessive yielding, that stiffness is lost, or for brittle materials, it's sudden fracture. Okay. And the isotropic case, what we do is, if the stress state is given, then we find the principal stresses, sigma 1, sigma 2, and tau 1, 2. And those come from the Mohr circles. So given the sigma x, sigma y, and tau xy, principal stresses have a very simple formulation. It says principal stresses are the average of sigma x and sigma y divided by 2, plus minus some difference of the stresses divided by 2 square plus tau xy square. Now, this is basically the Mohr circle approach, that given a state, you're going to be finding this, and tau max and tau min will be over here. So this is the tau axis, and this is the sigma axis. So this is the Mohr circles. Now, once we have that, sigma y and sigma 2, for ductile materials, we compare it with the yield strength. So if sigma 1 is smaller than the yield strength, we are okay. If it's larger than minus the yield strength, we are okay. And we also look at sigma 2, if that is also smaller or greater than the yield strength. So we're done with the if it's the brittle material, then typically there is a ultimate tensile strength for brittle material, which is different than the ultimate compressive strength. And these are properties, material properties, that should be given. So SY, yield strength, will be specified. And here, SUT or SUC will be specified. And then you do the same thing for sigma 2. And if they are within those limits, you're good. You don't fail. We can also do max strain failure criteria, in which case we look at the strain in along the fiber direction and strain along the, this is not isotropic, principal material direction, and strain along the transverse principal material principal stress direction. And then we make a plot of it in the stress space. So this is basically something like a sigma 1, sigma 2. This is stress space, and this is SU tension, ultimate tensile strength from here. Oops. And this is the SUC, ultimate compressive, and it's the same thing here, SUT, and as you see, in this case, this should be square if it is SUC and SUC are the same. Now, beyond that, there is some interaction and shear stresses come into picture. And this is the maximum shear stress criteria or threshold. And you again compute maximum shear stress from the principal stresses. And that will be equal to the radius of the Mohr circle, which is this thing here. And then you map that on the strength space, which basically gives you these lines that says, well, incidentally, this thing hardly like this. The shear stresses do play an important role in failure, which we'll actually see for fiber case reinforced material. It's going to be the same way. And so that eliminates this part of the space, yield stress space. So this is interactive. Shear and normal stresses are interacting. And the next level, which also copied in the case of fiber materials, is going into quadratic failure criteria. And there, the isotropic version of it is called von Mises distortion energy criterion, which basically the distortion energy given in terms of the stresses, sigma 1, sigma 2, and we also have, in case we have a three-dimensional problem, sigma 3, 0. For plane stress, sigma 3 will be equal to 0, and this term will disappear, and you'll get sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2, and then the sigma 1 2 square and sigma 2 square, so you get the 2's in there. And then if you go and make it uniaxial loading, sigma 2 also equal to 0, one axis loading, and the distortion energy is related to the yield failure with this fashion. But in case of biaxial loading, when you only have sigma 1 and sigma 2, it reduces to this thing, which basically, instead of being this curve like that, it's some sort of an ellipse that actually goes around like that. And if you look at the experimental data, it actually happens that that this von Mises is better than any of the other criteria, because when we do the experiments for isotropic materials, a different combination of sigma X and sigma Y, and then we compute the sigma 1s and taus and sigma 2s, you find that failures typically really do not go in here. They don't fail here. They failed before. So these will be like experimental data. And of course, occasionally there will be experimental data outside, but not necessarily coming here. So these, you hardly reach these points. You don't reach these points. The experimental data actually shows that you're mostly going to be around here with occasional data points in the experiments going outside the boundaries of the ellipse as well. Is it a perfect ellipse from the experiment? It hardly is, meaning that it probably more complicated with some chancy events, probabilistic failure events would also influence this failure in materials. So if we go to composites and we start with a single layer, let's say orthotropic layer, they are much stronger in the fiber interaction than perpendicular to the fibers. We basically then say loading parallel to fibers. In that case, strength is going to be governed by the failure of the fiber, either in tension or compression. And in a direction transfers to the fibers, the strength is governed by the matrix properties alone, nothing else. If you do stress analysis from given sigma x, sigma y, tau xy, obviously, just like isotropic materials, you can go ahead and find from this the principal stresses, sigma 1, sigma 2, tau 1, 2. But for us, they are useless. They do not coincide typically with the fiber direction. So instead of Mohr circle, we use transformation relation, which is the T matrix, okay, to find the sigma 1, sigma 2, and tau 1, 2. Again, repeating, these are not principal stresses. These are stresses along the principal material directions. Now, isn't there a chance that that combination is such that the stresses are way too large, not along the fiber direction, but slightly off 5 degrees, 10 degrees from the fiber direction? What happens then? Those questions will always be in the back of our minds. And you're going to see in some of the charts that we're going to do in the tutorial that, in fact, things can be somewhat complicated. Even if you do the analysis based on the sound analytical approach that we develop our equations. On top of that, of course, fiber volume fraction and other things play a role in the failure, plus how well the fibers and the matrix are bonded together. Is it possible that properties of the material is different around the fibers than right around the fibers than further away from the fiber, where matrix really starts taking? What I'm saying in another sense is this is a fiber, some matrix around it. It is possible that there is a region around this fiber that properties of this matrix here is different than the properties of the matrix here. So this is called an interface region between the fiber and the matrix. And there may be other things happening here that we don't know and we would not care as designers right now. So we're not going to use any micromechanics models that go into this level of complication. So what do? What we do instead is we assume everything homogeneous, matrix is homogeneous matrix, fiber is homogeneous fiber. The strength of a layer will always be defined in reference to directions parallel and transverse to the fibers. And maximum stress and maximum strains are about the principal material directions. So we compare stress along the fiber direction with the tensile strength of the fiber, and we call that XT. This is specified given quantity. If stress along the fiber direction is less than the tensile strength of a fiber, it doesn't fail. Then we look at stress perpendicular to the fiber direction, and we compare it with the tensile failure of the matrix, and that would be YT. Then we do the same thing for compression, and there's potentially a different value for the compressive strength of the fiber and compressive strength of the matrix. Though often Y's are closer to one another, YT and YC, than XT and C. There is substantially big difference usually between XT and XC. So X and Y are the outlet strengths parallel and transverse to fiber direction, X fiber direction, Y matrix direction. And as we said here, XT and XC can be quite different from one another. Sometimes even an order of magnitude is not unusual. Y's, on the other hand, the matrix is much closer to one another. That's the basic thing. And then we say, okay, if you really want to worry about shear, we can come up with a shear strength of a fibrous layer and give it to you. And then as long as you compute the shear stress in the principal material direction and compare it with the shear strength S, this is the in-plane shear strength of a fibrous material, then you're okay. Then you do the same thing that we did in the isotropic materials. You compared stresses with the strength material directions. If you want to do it strain-wise, you say, okay, epsilon 1, strain along the fiber direction must be less than tensile failure, strain failure of the fiber, which basically, from the relation between the fiber and its modulus, we write it to be xt divided E1, and then epsilon 2, strain perpendicular to the fiber direction, must be less than a strain at failure perpendicular to fiber direction. That is the matrix tensile failure strength divided by E2, which is the second direction modulus. And then similarly for the compressive case with the minus sign in front of it. And in the shear case, shear strain is basically a shear strength allowable divided by G1. All right, so that's the max stress and max strain for orthotropic gauge. What about interactive? Just like we did in Tresca. Well, we have interactive criteria, and also the quadratic failure criteria, and they're called Psi-Hill, Psi-Wu, and then there's the Hoffman's criteria. Hill is basically, Psi-Hill is the extension of the von Mises, and Psi-Wu is also an extension of the von Mises. Hoffman is literally quadratic, like the ellipse that we formed and this is the extension of the energy density failure criteria. All right, so what are they? Psi-Hill basically has this formula that says if you have a quadratic relation between sigma 1, sigma 2, and tau 1, 2, and you know the tensile fiber strength, tensile matrix strength, and shear strength of the fibrous material, some of these quantities must be less than or equal to 1 to avoid failure. If they are bigger than 1, you fail. If the stresses, this is assuming that the stresses are primarily tensile. If the stresses are primarily compressive, then we replace XT and YT in the Psi-Hill with XC and YC. And we're going to do this in the tutorial that we'll do in the next, hopefully 15 minutes or so. I don't want to spend too much time because you're supposed to be knowing these things, and it's just a simple failure criteria. You are given an equation and you go with that. The Hoffman, which is the really interactive quadratic criteria, has both XT and XC together. So you don't have to worry about the sign of the sigma 1 and sigma 2 and sigma tau 1, 2. And they choose either this or this to implement a failure criteria. This includes both XT and XC and YT and YC in there. So therefore, it can be used for any combination of stress values. And besides the quadratic terms, there's also linear terms in sigma 1 and sigma 2, which are the stresses along the fiber and perpendicular to fiber direction. Okay, so that's now once we have that, I guess I had this chart that I really don't want to spend any time. This is the Saibu, a more general form of the failure criteria. If you start with this Hoffman and then do some manipulations and put XT equals XT, YT equals YC. From this, we recover the Psi-Hill criterion. And then if F12, some people try to make it science out of it. And this is the more generalized form of it. I'm by no means trying to downplay their role. It's very important. But it's just, we don't do this in day-to-day engineering work. This is material science work. And we're not material scientists. We are engineers who will just get these strength allowables and use it however they are available to us. Then you can play with these things and do different things with them in terms of angular orientation of the fiber, where M and N are the cosine of the fiber orientation angle, sine of the fiber orientation angle, and find the values of sigma x. And we'll do this with Mathematica, so there's no need to go through derivation of these equations. But basically, to wrap it up, now that we know how a single layer fails, then we can go to multiple layer case of a laminate. And since every ply might have different orientation, then we have to basically do the analysis in each layer, stresses in each layer. If we consider in-plane problem, no bending, then strains epsilon x, epsilon y, and gamma xy are the same in each layer, but they are not necessarily the same along different fiber orientation areas. So you still find different orientation strains along different orientation layers, but at least stresses in the x, y, and the directions are the same. Strains are the same. Some layers may fail earlier than the others, causing load redistribution between different layers. So if one layer fails, you can basically assume that it's removed from the layup, and the remaining layers might be sufficient to carry the loads. Okay, and that's the reason why sometimes we don't care about matrix failure, because those layers are carrying very little load along those directions anyways. So we do not assume the failure of the matrix to be the failure of a laminate. Instead, we assume the fiber failure to be the main ply level failure, in which case still remaining layers might carry the load, but this is typically called first ply failure, and this is implemented typically after the first fiber failure in a given layer is detected. And then if the remaining layers are carrying the loads, this will be something like a load, say P versus displacement. So material will be behaving linearly. First matrix cracking happens, and sometimes you don't even see it, so you keep going straight. Until the first fiber failure happens, then you may actually start seeing its influence, that this becomes dropping or start moving in other directions. And you may still be able to carry load. And so this is the part where you're now doing progressive failure analysis, which means that the linear relationship between load displacement no longer holds. So this is a repetitive analysis, which means that it's like a nonlinear analysis, that you're doing the analysis again and again until you find the failure. So that's what's explained here. And you can read the rest of it faster than I can read for you. Whether stress-based or strain-based, we do the transformation to principal material directions of the strains, and then we do the same for the stresses and compare the different levels. And at the end, a picture like this might appear. What are we seeing here? This is sigma x and sigma y. And each of these lines may show failure of a certain orientation angle. And typically, they appear in pairs. That this is one, and this is the other one of the same orientation angles. And it says, you cannot be on this side. No, that was not the right one. You cannot be on this side of this failure line. And you cannot be on this side of the failure or that particular orientation angle, and that given laminate and given load combination applied to that laminate. Then you look at another layer, and let's say this is theta 2, and its corresponding negative 1 is again theta 2. So this is a plus minus theta 1. This is theta 2. And that says you cannot be on this side. And you cannot be on this side. You see, now we are starting to box the failure envelope. And you look at the other plies, and they will always also be coming in pairs. And eventually, you create the smallest envelope around the 0, 0 axis that you will be allowed to have stresses in different orientation angles. Okay, that's good. I should have done this maybe in another color, because there's another red line here, which I need to explain. So instead of red, I'm going to use the blue for that. But then again, there's this blue line. What this blue line shows is, for a given loading, when we increase the magnitude of loading from 0 to some higher and larger non-zero values, or apply them in the, so origin means your stresses are 0, 0. Based on your applied loading, as you increase the log magnitude, let's say lambda, you may be moving either in that direction or in this direction. So there's going to be a relationship between sigma x and sigma y that will be constant as you apply the loading. This is like a maybe pencil coupon, okay? And you have a bunch of angles in your laminate, and you're applying lambda load 0, lambda increasing, your stretch starting to stretch. So that will induce a certain ratio between sigma x and sigma y in there. So you might be moving along this line. And the trick is, where does this cut the envelope, and which orientation of the envelope are you cutting? So, for example, in this diagram, there's a third angle, let's say theta 3, and this is its counterpart in negative, and that basically says you cannot be on this side. So that's part of the constraining. So this one is either failing the layer with the plus theta 3, or failing the layer with, say, theta 2 here. It's not quite clear here. But here it's quite clear. It's failing this layer, theta 2, this one, not its counterpart of theta 3, which is this line. Okay? All right. So we're going to actually now look at the tutorial, but we're not going to do the laminate showing this kind of diagrams. We're going to do first single layer to see how the sigma x and sigma y envelope change, and how the different failure criteria. Well, actually, we're going to be mostly looking at Sahil, but how the different failure modes interact within the Sahil compared to the fiber and matrix failures independently. And then the tutorial on Tuesday, or if people don't show up on Tuesday for tutorial, I will do it on Monday for tutorial. I'll do it on Tuesday during the class. I'll do the tutorial number 4, which is going to be showing these kinds of diagrams for a laminate. Okay? I'm hopefully planning to finish my own routines that it will generate these kinds of diagrams automatically, not you doing it one by one. All right. Any questions so far about failures? I'm assuming that you guys will have some questions about failure, because it's such a, I don't know, fuzzy topic. It's really not an exact science. And you'll see some things in the tutorial that I'm sure will raise some questions from you. Can you fail from a positive theta value and not the negative one? Yes, of course. It will depend on the stress state in the laminate. In fact, this diagram shows that typically one is critical, the other one is going to be far from being critical. You have the. Let me do a simple diagram here. Let's say, oops, let me get my pen. So I have a laminate, and I'm applying some NX bar here, and some NY bar there. This is NX bar, and Y bar, and Y bar, and say NY bar is a function of NX bar, so some alpha, let's say 0.3 times NX bar. They are not independent loading, but under given load increment, both NX and NY increase. So with this combination, a ply which has a plus 30 layer might be going like this, minus 30 will be going like this. Stresses along this direction are going to be very different than stresses along this direction. So this may fail, whereas this will be far from failing. Does that answer your question, Alex? All right, very good. Any other questions? If not, let me go ahead and open my tutorial on failures. And let's minimize this. And again, this is also on Blackboard right now. Where is it? Failures, I hear. Okay. Okay. Let's make this way. 200 is 200 a good size, or should I make it a little larger? I can go to 300. All right, that's 300. Let me make this also a little longer. And as usual, I will need to open CLT. I think we're on version 1, right? Let's check. Let me check if I have version 2 already. Programs, version 1. Yes, version 1 is the latest. And the reason why I'm opening this is, of course, I need to load my program for composites, run all the code. I did run all the code now, so I can move that to the background. And with that, if I type question composites, it should recognize, yes, it does. So it means all of these are in place. So I need the stresses in an orthotropic apply under the uniaxial loading or some biaxial loading or tensile or compressive stresses. And plane stress, sigma x, sigma y, tau x, y are given. Plate thickness is given. So I can have stress at A, point A might be just sigma x 0, 0. These are just labels. I'm assuming that sigma y and tau x, y are 0. Okay. This way, I'll be able to orient my fiber from the x and y direction and see what's happening along those fibers. So stress state is not changing with my fiber orientation angle. I have the same stress state in my, let's say this is uniaxial coupon, and I applied stress. Given stress, say it's equal to sigma x. So stress A is sigma x. Sigma y is equal to 0, tau x y is equal to 0. Then I need the transformation matrix so that I can find the sigma 1, sigma 2, tau 1, 2. And basically, T matrix, I leave a variable angle A and G in degrees. So orientation is A and G in degree angles, so that I can make plots of these stresses along the fiber and transfers to the fiber directions. And my sigma 1, sigma 2, tau 1, 2, then that product of T mat dot stress at A. Okay. So this is sigma 1. This is sigma 2. And this is tau 1, 2. These are the stresses along the fiber direction and perpendicular to the fiber direction, and shear stress in the 1, 2 fiber direction axes. Okay, I don't know if I needed to put this equation there, but that equation was from one of the tutorials, so I might as well maybe put that. also in here. No, from the lecture I can put it. Stress. Plane stress. I thought I had that relation. Oh, here. Sigma 1, sigma 2, tau 1, 2 is T times sigma x, sigma y, tau x, y. I don't know if you need to. Why not? I'll copy that and put it in there as well. It would be useful. All right, some text is going to be nice. Don't I have any text in this tutorial? That's funny. I don't have any text. Anyway, so this is the this relationship with the T matrix being m squared n squared to mn. That's T matrix, and then this is this sigma 1, sigma 2, tau 1, 2. So I have this sigma 1, sigma 2, tau 1, 2 with sigma x some value and angle being some value. Now, if I define my psi hill says sigma 1 squared divided by xt, sigma 2 squared divided by yt, minus sigma 1, sigma 2, xt. Basically, this is psi hill. And I did not put any text in this tutorial. I am curious why, because I should have at least put some text, if not maybe the equation for it. Let's put the equation from the lecture. Psi hill. All right, let me copy that. In fact, why don't I copy it together with the text so that I don't have to type the text? How about that? All right, so I ignored the 1 here. So basically, I'm computing the left-hand side here, and that'll be my psi hill number. But I can get that symbolically. So this is symbolically in terms of sigma x, apply the stress level, and the strengths, xt, yt, ss, the shear strength, and the fiber orientation angle. I can collect all the sigma x's in this equation together. So I redefine my psi hill by collecting all the sigma x's together in my psi hill equation, which basically gives me this. It says sigma x squared times this quantity. This is completely in terms of angular orientation of a fiber, and its tensile and matrix direction strength and shear strength, SS. Then I can solve psi hill when it's equal to 1 for the value of sigma x. I'm basically defining the value of sigma x here when I equate this whole thing to 1, okay? So this is the value of sigma x, the failure value, depending on the XTs and the angle orientation angles. And the solution comes in a pair of two solutions, plus and minus, sigma x, since it was square. So I take the second term, which is the plus version, and make it the solution equals sigma x of the second. So this is the value of sigma x. I determined the value of sigma x. Here I need the values of strength, xt, yt, SST, but strength typically I also do xc, yc, and ss. And I do this as conditions that xt has a value of 1260. I didn't use any units, so we have to use some units. Let's say megapascals, and you have to do your stress analysis accordingly for that. So my strength is basically a bunch of conditions. That xt goes to 1260, xc, yt, yc, ss. Then I take the solution. This is my solution again, just in case. I need to place it here. This is the solution. And substitute the xt, yt, and the ss into this solution, and change rename the resulting equation plot x. And if I do that, plot x comes out to be a function of only angles. And then I plot that angle, plot that stress level at failure. This is now stress level at failure, plot x. As a function of angle from going from 0 to 89.90. When it's exactly 90, there's something goes to infinity, so it's not nice, and you'll see perhaps what might be happening here. And then I arranged ticks and so on and so forth so that you can see the different angular increments. But basically, this is the failure envelope for a single layer with orientation angle stretched along the axis sigma x and failure load on the vertical axis. So a layer with 0 degree angle is going to fail up until this level, which is about, I suppose, 1250 megapascals, let's say. But if I change the orientation angle to 15 degrees, look at how fast the strength is decreasing. Okay? So I'm stretching along the x direction. My fiber is 15 degree orientation. Strength is reduced very substantially to here. 30 degrees down here. 45 degrees, 60 degrees, 90 degree layer will fail at the lowest level of stress applied sigma x. Okay? So this is what Cy Hill tells me. Now, how does this compare to strength directly along the fiber direction and directly along the transverse direction and shear strength? Let's compare that. Let's make that. So I can define a new label, sigma 1. This is the SIX. This is the stress along the fiber direction. That's going to be at failure that I'm going to do, because I'm going to be evaluating its strength. And I'm going to assume the strength divided by cosine of the angle to be my strength value, or stress at failure. This is the fiber direction failure. This is transverse to the fiber failure. And this is like max stress criteria. This is psi hill, which includes the interaction between sigma 1 and sigma 2 and tau 1, 2. These are stress allowables directly based on the stress failure along the fiber direction. So these are the allowable stresses, sigma 1, sigma 2, and sigma 3. This is due to fiber failure. This is due to matrix failure, and this is the shear failure. And then I plot, along with plot X, these three, and color them to be red is the psi hill, green is red RGB, red, green, blue is the fiber direction failure, green is the transfers to the fiber failure, and some color between 1 and 1, the green and blue, I think something like a strange color, will be the shear failure. So if I make those failure loads, this is what I get. So what is this telling me? If I assumed max stress criteria based on fiber failure, this is how my failure envelope will change. That as I change my fiber orientation angle from 0 to 90, if fiber failure allowable load is increasing. The green one transfers to the fiber. And it says, hey, you don't fail until maybe you reach some 15 degrees or so. At 15 degrees, this is where you're going to fail the matrix. But my psi hill says this is red one, is the envelope. So you see actually psi hill takes into account this interaction between the stress along the fiber direction and stress in shear. This is the shear. If I look at only shear value, failure is due to shear, this is how my curve changes. So, in fact, if I ignore the red line and make my failure based on fiber orientation failure angle, max stress, max transfers to the strength, it will tell me that by about 2-3 degrees, my failure load is about here. Whereas psi hill tells me it's already down here. And this agrees with the experiments much better than these points here. So experiments actually agree with this psi hill red line much better than these. These lines say you're not going to fail if you have 75 degrees. You're not going to fail the specimen in shear until you reach this. But you're going to fail due to transverse direction here, which agrees with psi hill. At about 45 degrees here, max shear stress says you won't fail until here. Max transverse stress says you won't fail until here. But this criteria that takes into account the interaction between these two says you're going to fail here. And this agrees with experiments better than these lines. That's why we like psi hill, or the version of it psi vu, better than the max stress and the max strain for laminates. This is what it shows. What if we have a compressive stress? This was a tension case. In that case, I'm going to do my psi hill differently. I'm going to write it in terms of XC, and YC, which based on my strength, they have different value. XT has a value of 1260, whereas XC has minus 2500. So it's almost twice as high in absolute value compared to the tensile failure. Shear, the transfers to the fiber direction is not that big. Although in this case, actually, it's 3 times as large. But the real big differences, as I said earlier, for most materials are the XT and XC. Anyways, so if I use those in my psi hill, which was was my psi hill in terms of XTUIC, and I do my psi hill. Compression values. I redefine psi hill here and collect the sigma x is there again. Square is here. These are the compressive values and shear. Again, solve and find the envelope. I equate it to 1 and solve for sigma x. Therefore, my solution is the second of the solutions. And if plot x sub c is now the compressive one, and I do the same thing together with this is now the compression value of psi hill, compression version. The axis actually goes more than 1400, so I'm going to make it 1600. And more, actually. Let's say 2000. It's still going 20. Oh, at 0, was it what, 25? What was it? 2500, yes. So this is a compression one at 2500. If I do the same thing for the max stresses, max stress criteria, and make this 2500. Again, this is what I get, but this time my colors got mixed up. RGB reds, blue. Oh yeah, I know why blue doesn't show. It's above actually. And then green, and then 1-1. One of them should be appearing. Oh, plot X. This is the tension one. I need to remove the tension one. I don't need the tension one. So dark blue, which is the fiber failure, actually doesn't even show in here, because I think it will show higher than that. So if I do this 3000, it shows itself at 2500. And same thing again, psi hill behaves much better. Now let's go to biaxial or with the shear included or without the shear included. You can include also the shear. But now I'm making stress A to be sigma x times some ratio R or alpha times sigma x. And shear is 0. Okay. And this is my stresses. This is my psi hill. Collect the psi sigma x's. Solve for the psi hill. This is biaxial. This is solution. It has a ratio and also the angle. And I'm going to plot it with plot x again. And for comparison again, I'm going to use max stress criteria. And it says sigma 1 equals to xt, sigma 2 equals to yt. So that's the failure based on the max ratio. And this is the failure again for value and the strength is specified. And then I'm going to use manipulate and let the load ratio R to be changing, or R ratio. And this is what I get. So for R equals 0, this is what I have. when I'm moving to biaxial case, there's sigma x and also, let's say, 0.05 times sigma x as sigma y. So this is the value of sigma y is increasing. Next 1.1, you see this is the side hill, and how irrelevant this is for biaxial case. How irrelevant this becomes. So these two mean nothing. This one, transverse, is starting to control almost right away. So even with 0.05, transverse failure is taking effect. And as I increase this, our ratio for biaxial, transverse failure completely overtakes, and fiber failure here and shear failure has no influence as I increase my alpha. You could have also provided a beta value, just like in your homework assignment. So we'll make this thing to be instead of alpha, this R ratio, I can call this, I don't know, it's a G ratio. So this is beta. And do my stresses in terms of sigma x, alpha times sigma x, beta times sigma x. It's like your homework assignment. And then basically this is going to be your stresses. More complicated. And then you will have two parameters that you can change, alpha and beta. Or you can create a two-dimensional graphic surface. Surface contour of the failure envelope for sigma x and sigma y. Consider that for your homework problem. How is that? How is that for a homework problem? So that's it. That's all I have for today. These are very useful things. The subject is, as I said, not the most inspiring subject in terms of design engineering, but we have to know these things. We have to understand these things for design engineering because of the fact that you have to design for failure, which we will do, I guess, next lecture and tutorial. That's it, gentlemen. If no questions, you have a wonderful time for the rest of the week. Have a good weekend.